Hello everyone, welcome back to the control system engineering lecture. In this lecture, we are going to study about how to convert a state space equation into a diagonal canonical form or a Jordan canonical form. We know that a diagonal canonical form, the matrix A of a state space system is have the diagonal form where the diagonal element of this matrix actually represents the poles of the system. Like this. If there are three poles like P1, P2 and P3, the A matrix of your state space equation into a diagonal canonical form are represented like that, where the poles of the system is equals to minus P1, minus P2, minus P3. The similar representation of the form when we have a repeated pole, multiple pole with the same value, then this form is actually represented by a Jordan canonical form, where the diagonal element are still the poles, but only thing will change are these values. For an example, for a repetition of pole s equals to minus p1 and minus p2, we will have a matrix in this form: minus p1 0 0 0 minus p2. So this we have studied into a last lecture. So this is called the diagonal canonical form, and this is the Jordan canonical form. So we will see that how to convert a state space equation into these particular form. These form are basically helpful when you have like to analyze the stability of the system by looking at the poles of the system, which are available in the right hand side of S plane or into a left hand side of S plane. So let's start how to do that. Let's say we have a state space x dot equals to ax plus bu, and y matrix output is equals to cx plus du. If you choose a matrix x such that x equals to pz, transform a matrix in this form, then the x dot is equals to pz dot will be equals to apz plus bu. Okay, so if I represent this in the z form, we will have p inverse apz plus p inverse bu. Similarly, the output y will be equals to p c into p into z plus du. So now what we want the value p inverse ap such that it is into a diagonal form, and we know that the characteristic equation of any state space system is represented by si minus a, determinant is equals to 0. If you solve this equation, you will have the poles of the system, and the same equation is nothing but it is used to find out the eigenvalues of the system. So the p inverse ap should equals to, let's say we have lambda 1 0 0 0 minus lambda 2 0 0 0 minus lambda 3, where lambda 1 lambda 2 and lambda 3 are the eigenvalues of matrix A, which is actually calculated by the lambda I minus A determinant should equals to 0. So lambda is equals to lambda 1, lambda 2, lambda 3 if you solve this equation. Okay, so what is the value of P matrix? We can only have P inverse AP is equals to in this form if we choose a P matrix such that P equals to 1, lambda 1 square, 1, lambda 2 square, 1, lambda 3 square. This is for a 3 by 3 matrix. If you have n by n matrix, then you can have a P matrix in this form: 1, lambda 1 square to the lambda 1 to the power n minus 1. This depends upon the vector length, state, how many states you have. 1, lambda 2, lambda 2 square, lambda 2 cube, and so on, lambda to the power n minus 1. Similarly, we will have lambda 1, lambda n square, and up to the lambda n to the power n minus 1. This is the case when you have distinguished root lambda 1, lambda 2, and lambda 3. And if you choose the P matrix in this form, the P inverse AP will always be in the diagonal form. So if I represent this equation, this state space equation into this form, z dot equals to A hat new A matrix with the state z plus B hat new B matrix with U, and output y equals to C hat into z plus du. You can see that d is same in both the cases. So the A hat matrix is equals to P inverse AP, which is always be equals to the into a diagonal form minus lambda 1 0 0 0 minus lambda 2 0 0 minus 0 minus lambda 3. The B hat matrix will be equals to P inverse B. You can solve this equation. You have P matrix and B matrix you will have, and similarly the C hat matrix is equals to C into the P matrix, and this will give you the CP matrix. Similarly, there is another special case. If you have eigenvalue lambda, a repeated eigenvalue lambda 1, and lambda 2, you have two same eigenvalues, then in this case it is not possible to represent your matrix A into a diagonal canonical form, but instead you can represent this form into a Jordan canonical form. So in this case the P inverse AP will come into the Jordan canonical form, which is the lambda 1 1 0 0 lambda 1 0 0 0 lambda 2. And in that case the P matrix will be a slight different. The P matrix will be 1 lambda 1 lambda 1 square. The first column will be same, but for a repeated value we will have 0 1 2 lambda 1. Similarly, the third value is distinguished. This is a different value, so we can have a normal lambda 2 square, and we will have the new P matrix like this. Similarly, if you have a 2 by 2 matrix, the P matrix can be written as 1 lambda 1 0 1. If you have eigenvalue lambda 1 and lambda 1, both case to have two same values of lambda 1. Similarly, you can also decide for the more order matrices. And the B and C matrix will have the same formula. Only thing is will be different is the P inverse AP matrix, which is the A hat matrix, will be this form. P matrix will be this form, and B matrix you can calculate by using the P inverse B, and C hat matrix will be CP. Okay, so let me do a question on that, so it will make you more clear about the concept. So let me take an example. X dot equals to, we have 0 1 0 0 0 1 minus 6 minus 11 minus 6. This is the question we have given, plus B matrix, it is given as, if you check it, 0 0 6 into U. Output Y is given as 1 0 0 X. D equals to 0 in this case. So for doing this, we have to first find out the eigenvalues of the system for making the P matrix in diagonal form. So the eigenvalue can be found out by using the lambda I minus A determinant equals to 0. We will have the equation. By solving this equation, we have this value lambda 0 0 0 lambda minus A 0 1 0 0 0 1 minus 6 minus 11 minus 6. The determinant of this matrix equals to 0. If you solve this equation, you will find out the third order equation of a lambda, and you have three values, -1, -2, -3. So we will have three eigenvalues, lambda 1 equals to -1, lambda 2 equals to -2, lambda 3 equals to -3. So then in the next step, we have to decide what is the P matrix. So the P matrix will be 1 lambda 1, which is -1, lambda 1 square will be 1, 1 lambda 2, which is -2, lambda 2 square will be equals to 4, 1 lambda 3 -3, lambda 3 square will be 9. So this is your P matrix. So we do not have to calculate the the A hat matrix, because we know that the P inverse AP matrix will always into a form of a diagonal canonical form, because we have a distinguished eigenvalue. So we will have -1, 0, 0, 0, -2, 0, 0, 0, -3. These are the three eigenvalues of matrix A we have. So the A hat matrix will always be in this form. The B matrix you can calculate P inverse into B. If you solve this equation, please solve by yourself. Use the P inverse of the P matrix, and the B matrix is given to the system, which is 0, 0, 6. If you solve this equation, you will have the B hat matrix equals to 3 -6 and 3. I will leave this exercise for you. Please do the needful. Similarly, we have the C hat matrix will equals to C into P. We have 1, 0, 0, and the P matrix we know that is equals to 1, 1, 1, -1, -2, -3, 1, 4, 9, and we have C hat equals to 1, 1, 1. So the new diagonal form of the given system will be Z dot equals to A matrix, which is equals to -1, 0, 0, 0, -2, 0, 0, 0, -3 into Z plus B matrix, which is the 3 -6, 3 into U, and finally the output equation Y equals to 1, 1, 1 Z. D value was previously 0, so we'll have this equation, diagonal equation. Okay, so this is how we actually convert an equation into a diagonal form or Jordan canonical form. Similarly, you can try for the Jordan canonical form. If you have a repeated pole, if you have two repeated pole in this form, you can use 2 by 2 P matrix like this. If you have two repeated pole and P matrix is in this form, you can use a P matrix formula for this in that case. And you will have A inverse AP into a diagonal canonical form. In the case of distinguished root, we have diagonal matrix, but in the case of similar root, we have this one in upper triangular of this matrix, lambda 1 and lambda 2. So this is about the conversion of state space to a diagonal canonical form or Jordan canonical form. Thank you very much.